Hello and welcome to Psycho, Science and Coding. This is the first part of a video series where you will learn about quantum machine learning, and in the end you will be able to code your own quantum neural network using Python and PennyLane. Each video will be roughly 10 to 15 minutes long, and about half of the video is theoretical concepts and the other half is hands-on coding in Python. At the end of today's video, you will know what a qubit is, be able to describe the computational basis states of a single qubit mathematically, and simulate a qubit in Python using PennyLane. We will start at the very basics, the fundamental unit of information in quantum information science. That's the quantum bit, or qubit for short. We know that a classical bit can be either in the 0 or 1 state, which are both integer numbers. Similarly, a qubit can exist in the states 0 or 1. I will explain the weird notation in a second. A first difference to classical bits is that the state of a qubit is not described by an integer number, but actually by a two-dimensional vector, a complex one, so the components of the vector are complex numbers. The space c², where the qubit's states live in, is called a Hilbert space, named after German mathematician David Hilbert. So now for this funny notation. It's called bracket notation, also referred to as Dirac notation, named after the famous British physicist Paul Dirac, who introduced it. It's widely used in quantum mechanics and very handy, as we will see later in the video series. And the thing we saw before, when I introduced the two states, is called a ket. For now, whenever you see a ket, basically just think of a column vector. Now let's see what the 0 and 1 states actually look like, in a specific basis to be mathematically precise. Usually, 0 is represented as the 1, 0 column vector, and 1 as the 0, 1 column vector. So indeed, those are just two-dimensional vectors, and since their components are integers, and integers are a subset of the complex numbers, these are also complex vectors. The two states, 0 and 1, form a basis of the Hilbert space that we have introduced before. In fact, it's the standard basis used in quantum computing, and is therefore called the computational basis. And here we will switch to the coding part of the video and start simulating qubits in PennyLane. For this tutorial, I'll use Google Colab, but feel free to use your own Python IDE or environment. First, we install PennyLane using pip install. In notebooks, you have to include an exclamation mark, so that the command is executed in the underlying shell rather than in Python. Next, we import PennyLane as QML. QML stands for Quantum Machine Learning, and it is the standard alias you will see in the official documentation. I will print the version I'm using. In PennyLane, every quantum computation runs on a device. So first, we'll instantiate such a device. We call qml.device that returns the device object, which is the backend that executes our quantum computation. This backend can be a simple simulator or a real quantum device. For today, we'll use the basic simulator default.qubit. We simply pass the device name as a string to the name argument of qml.device. And we also specify how many qubits we want using the wires argument. We are starting with a single qubit, so we set wires equals 1. Next, we define a Q node. A Q node is a special object in PennyLane that combines a quantum function, that's the quantum computation we want to perform, with a device, which is the simulator or hardware that runs it. We start by defining the quantum function and turn it into a Q node afterwards. So first, we define a plain Python function. Let's call it qubit, since we want to simulate a single qubit with it. In the function body, we assign qml.state to a variable which we call state. In PennyLane, the state method tells the simulator to return a full quantum state vector of the system. Finally, we return state in the function body. And that's it. Almost. We still have to turn the function into a Q node, which we do by using the decorator at qml.qnode. This turns our qubit function into a Q node. When we call the function, PennyLane builds the quantum circuit, runs it on the chosen device, and returns the result just like a normal Python function would. We also pass the device from before to the device argument of the decorator, so PennyLane knows where to execute the circuit. And that's it, this time for real. Now let's see what the state of our qubit looks like. We simply print the output of the function via calling it like a normal Python function. This looks interesting. But if you look closely, that's exactly the zero state we defined earlier. Python shows it as a one-dimensional array, which looks like a row vector, but it actually has no specific orientation. And in fact, we can also see that the state is a complex vector, as indicated by the +0.j. This is Python's representation of the imaginary part of a complex number. The reason we obtained a zero state and not a one state is that PennyLane initializes all qubits in the zero state by default. You might now wonder, how can we prepare the one state, the second computational basis state? At this point, let's do a quick teaser. We can apply a quantum gate called the X gate, also known as the Pauli X gate or NOT gate. It flips the qubit state from 0 to 1 and vice versa, just like a classical NOT gate flips a bit between 0 and 1. In the code, we simply call PennyLane's QML.x method before the call of the QML.state method, and we tell it which qubit to act on using the wires argument. Since we only have one qubit and qubits are 0 indexed, we pass 0 to the wires argument. Now if we print the output of qubit again, we get something different. This time, the 1 is in the second component of the vector. That is exactly the one state we defined earlier. This was just a small preview of what's coming. In the next video, however, we will look at one of the most fascinating quantum properties, superposition. We will explore general single qubit gates beyond the computational basis and visualize them on the Bloch sphere. So to wrap up, let's summarize what you've learned today. You now know what a qubit is and how it differs from a classical bit. You know the computational basis states 0 and 1 and their vector representation. You know how to simulate a single qubit in Python using the PennyLane package. Finally, you know how to use a simple quantum gate, the X gate, to change between the qubit's basis states. For reference, you will find the code from today's and future videos in my channel's GitHub repository, which I have linked below in the description. I've also included some additional resources for self-study and experimentation to help you deepen your understanding of the concepts and code we have covered today. And with that, I thank you for following along and hope to see you in the next video.